of them. First thing I did was add in the reasoning why we choose e to the number x. Why we do that is that we could get imaginary shit. We can get sine and cosine as our answer, which is otherwise known as cis, which I explained in the previous somewhere. Oh, I also did change the layout. I deleted all the calculus and the geometry. I'm going to expand this. I'm going to make more sections because I realized it's very dense in the geometry and trick section, and I moved it all the way to rotating bodies, so it makes more sense to be here. I need to clean it out a little bit. It's a little bit rough, mainly due to uh, me. It's also in the Jacobian section. I'm probably going to add one more question over here to make this look cleaner, and then I'm going to look at the Jacobian section real quick. Jacobian is over here, I believe. Let me adjust this one. It's always it's a little dense again, but it's better than before. I set up the uh, one over here with the Jacobian for sphere, and then another again. Did I? No, this is the cylinders. Yeah. So I add one over here and I add one over here where you use R because R is easier to digest, and then I add something about the pi circle over here. It didn't really. I just moved things over. I realized that probably was the best place for it. Another thing I'm gonna start working on is this for second order. This thing I'm gonna convert all of this into this format because this looks too messy in my opinion. Oh, what else do I want to say? Oh yeah, I was gonna talk about my second order shenanigans. So second order. So the explanation is when you plug in, because it can be cosine and sine, which means, as you know, there's only two solutions for a second order solution because there's two constants we need. That's the main reason that all these problems exist. We'll see why they diverge later on. Actually, I think the only way that that's not possible is if we have something like this, where we have mg over here, or where there's two constants here. So you see how there's two constants. That is necessary for a second order equation because you need to have two boundary conditions to actually solve a differential equation like that. So what does that mean? When you go over here, and because these are linear and second order, that's what we need to know. As you can see, I plug in the solutions to get this formula. This is why the quadratic formula, which I mentioned is some weird name, I forget. Uh, Let me go to the quadratic formula section. Is it, no, that's the limit section. That's the, I think simplifying polynomial. No, this is, yeah. So I call it the Balgashian Alcott formula because that's what the people that made it. I can never say their name, so I'm not even gonna try. I'm just gonna say that's what it is. But yeah, so let me go back to my second order section. So what I did was divide them into three groups. So over here we start with two wheel solution, kind of obvious what would it be, and this will define everything basically. Because of how second order all both wheels works, is basically just explosion like this usually, or decrease like this to zero. Critical points like that if it's a negative r, and that's what happens. And if you're talking about how it would represent in a pendulum or mass and spring, what happens is that it just slowly increases and just breaks off. It's imphysical, but it can happen if you have forcing in it. Um, yeah. The other one is two wheels. This is a case where it's also something like critical, but I need to put an X here just because we need basically what happens if you don't have an X is that C1 and C2 because becomes 1 and it returns to C1. This is impossible to have a second solution that is possible by looking at the solution. It is possible to have an X there. And the last one is basically this. Um, Very interesting. I did prove how it works. the imaginary part over here, I, just as a number, so you can just plug it into C2. But in reality, y is still, when you plug in the number, is still like a positive number that's not imaginary. Well, that's due to we changing to the Cartesian plane instead of the imaginary plane. Imaginary plane has a line over here and a line over here, and it works as a Cartesian, basically. And then when we turn into a Cartesian plane, we don't need that Cartesian, so we just have a sign. um, that's the reason why. Another thing is I just put all the explanation there, and then we do another one that has no x, just y. Usually with these equation, I have x over here, but if you don't have that, you can actually get away with just doing an integral, and doing integral to get this, and doing the other method to get all of this. Now, why did I change it constant 3? Is because this is a constant with no t. This is the constant with no t or x, depending on which is the dependent variable is for ODE. Um, so we can change it to C3 and make it all work. So this is the final conclusion you should get. This would be, what's the right word? A correct answer, but not simplified enough to make it readable. It's not readable, especially when I add the boundary conditions, which I really didn't do. Um, yeah, I should probably do this. Yeah, I forgot about this entirely. Let me just change this over here. So what I need is to derive this and then get the t over here, and then you can also kind of see how um, the e's can cancel out to get a regular polynomial. It's pretty easy to get a regular polynomial. It just cancels out because the mu usually or something like that happens. It just divides it out. The exponential whatever happens. That's a derivative. So why it's important to clean it is not important. It's just easier in my opinion. It's not really that important, honestly. Um, you can do it the other way if you want. Am I doing this wrong? Yes, I am doing this wrong. It's negative 6t, and this constant keeps on going. So this constant proves with VO, VI that this would be, if I plug in 0 over here, 0, that is 1, right? 6t, and then this is 1, and then so C2 equals, you kind of see how this works. I need to bring up Desmos. Did I get that right? Desmos, yes. And you bring up Desmos, and then you just have to do 1 minus 8 divided by 6. I'm not doing that in my head, so let's just do this. 1 minus 8 divided by 3 divided by 6. So there's your answer. Let me. I don't like it. Give me a pencil and paper. I'm just gonna do this real quick with a pencil and paper because let me get, if I have a pencil and paper somewhere. I just didn't like how it was a number. I just rather do it with pencil and paper and get something much cleaner. I can really easily get something much cleaner. 5 by 6, so it's 5 divided by 18. Is it 5 divided by 18? Negative 5 divided by 18. Yes, that is it. Let me really get a piece of paper. Yeah, sometimes graphing calculators are still not the way to go. In this case, it was not the way to go. I'll double check this when later, but now we need C3, which you get with y0. I forgot I made it like this. Pain in the ass. Let me just change up that. Okay, so now we have a case where there's 0, 0, so this is 0, and then this is 0, like before. This is 0, so this is 1. This is minus, so C3 is therefore equal to 5 divided by 8. See how clean that is? I don't have to do 2.7778 shenanigans. So now I can add this to here to get my final answer of this weird ass answer. I will have to double check that, but you could easily double check that by saying, okay, 0, 0, that is 1, so that's negative, so that's a 0. This if you plug in the initial condition of this. Now let's check this one when we have, where was it again? I didn't really re-put it in here, so the derivative, let me just check, let me put this in here and just check. So if I have 0, 6 is 6 divided by 18 is 5 divided by 3. Something's wrong. Why is it not working? It is not working. Why? Did I do something wrong here? If I had 0, I have 3 divided by. Okay. Oh, you need 1, so it makes sense. Yeah. So that's 5 divided by, and then 8 divided by 3 minus 5 divided by 3 is 3 divided by 3, which is 1. Yeah, it makes sense. So I can just delete this now. Um, that's how you double check it. Just plug it back in and see what you get. Um, yeah, I forgot to do this part, so good job catching that. And then, oh yeah, now, do I want to add this here? This is more like, well, I will delete it for now. We don't need to know about that. Now we're doing this question that I made, which I'll talk about later. It's a very basic question. It's not really that great. In fluid mechanics, it will be cleaner and better and makes way more sense than what we're doing right now. Um, yeah. Why don't we clean up something else? Unless we don't. How much time did I waste on this one? 12 minutes. Okay. We'll just waste time on something else now. Aka cleaning up this maybe. Oh, this is such a mess. Honestly, what was I thinking when I was doing this? Um, yeah, up to here is everything's good. Up to here, I can safely say it's makes sense at least. Uh, when it goes to geometry, let me get rid of the calculus because I removed the calculus proof. It was why am I doing that? Um, yeah, always give credit to the people that made this. That's for sure. Now, what did I want to do? Yeah, especially this one. This guy made a really good tape, good visual. It's probably better for later on in the physics section actually, but neither here or there. Oh yeah, I also did this over here, simple differential equations. It looks pretty good. Oh yeah, so I don't really need to focus on this because we already did most of it already. Why are we doing max and min in here? Okay, whatever. We did max and min over here too, I guess. Yeah. Okay, I'm just gonna turn off the computer now. No, 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 the recording so I can do other shit. Um,